Okay, picking up where we left off, we're on page 16. We're getting ready to talk about a new topic, which they have basically labeled additional factors, things to think about with regard to packetization. So most of the internet traffic is in bursts. If you look at, there's a cool little diagram here where this user might be using the internet. This is like a time scale. And this user has some stuff, and this user, so basically it's in bursts. Unless you're like listening to music or watching a video, if you're just surfing the web, that's all you're doing, then the data coming to your house or to your phone or whatever is in high degree of activity and then nothing. And then high degree of activity and then nothing. Long periods of nothing. So the idea is that if I combine all these users together, no one's really being put out of sorts, so to speak. In other words, this guy is not impacting this guy, and this guy is not impacting that guy hardly at all. I can combine these three patterns together and without really influencing the other. So that's pretty cool. So you might think, well, wait a minute. What about continuous streams? What about video or music? Well, it only appears to be continuous. It really is broken up into packets, and the packets are sent, and they're kind of, a few of them are kind of cached up on your machine. So if there was a temporary issue with somebody else downloading a file or consuming that bandwidth, when they're done, it'll just pick up and cut up the slack. So the idea is that, yes, even though it kind of looks like it's continuous, it really isn't. It's broken up into chunks. Okay. Circuit switching. Obviously, there's a tremendous amount of overhead. I mean, how long does it take to create a circuit on the phone? Not much, a couple seconds. But let's say all I wanted to send you was a number, okay? So think about this from a phone perspective analogy. I would dial this number, wait for it to connect, and then I would say 12, and then I'd hang up. And then 5 minutes later, I'd dial the number over again and say 13, and I'd hang up. That's not very efficient. The amount of data I'm sending is insignificant compared to the amount of time it takes to set up that connection, transmit the data, and then set it back down. Using packets, packets are typically rather small, and there's a little bit of overhead, obviously, and putting things in envelopes, so to speak. But it's kind of one of those necessary kind of things. Okay. So they talk about aggregation. So I'm aggregating data, which is kind of another way of looking at it is when people are using this kind of a scenario, I'm adding all their data together. It produces a pattern. This is kind of a waveform. This is one from the book talking about a particular university. And different times of day and different days of the week, their traffic basically goes up and down, and it's got a lot of spikes in it. It's not smooth or anything because they've aggregated all this data together. So if you were trying to come up with how to build a network for this university, they have the maximum number of incoming, the maximum number of outgoing, what the average is for outbound and inbound. I'd probably build a network that would probably handle about that much. In other words, I have to aggregate all of the sources in order to decide, how robust my network basically has to be. So when you do aggregate, you lose some of the bursty kind of information. There are bursts in there, but I'm aggregating it over long periods of time, so I don't actually see the bursts. Okay, there's a figure 1.8 on page 17. Basically, talks about this. The next thing is they talk about Moore's Law. And Moore's Law talks about scalability. And I'm not going to go into details of what Moore's Law is all about. It's basically the one that basically says that, every 18 months or so, the processor gets smaller and smaller and faster. Okay. What that basically means here is, if you're expecting 20-something% growth, you basically have to build your network with that kind of growth in mind. You can't say, well, there's only 5 employees here, so I'm just going to order 5 phones. You can't think that using a phone analogy. You have to be thinking about, well, yeah, but I'm, in about 3 or 4 years, I may have 100 employees. So when it comes time to ordering phones, maybe I should order 100 phones, right? So thinking ahead about Moore's Law. Okay, kind of leaving that behind. Now they're talking about layering. So on page 18, they talk about why things are broken up into layers. And it's basically separation of responsibilities and functions, the practice of arranging functionality in hierarchical layers. Oh, wow. Doesn't that sound important? Basically what they're saying is, if this was a human kind of a scenario where, I have the CEO and the vice president and manager and worker, it's all just a hierarchy. And so the worker does things and the manager hopefully does some things. And, each one of these things have individual roles. Now, in the computer world, it's essentially the same thing. I have a browser and I have the Windows operating system and I have a print driver in my printer. So let's say, for example, that let's talk about that one for just a minute. If I swapped out my printer, do I have to go back to Microsoft Word and Notepad and Internet Explorer and Edge browser? Do I have to go to those applications and tell them about this swap out? I don't, do I? Because all I need is a print driver. I just swap out this one piece. And that way the Windows operating system can take care of it. I don't have to talk to my applications at all. In fact, Notepad doesn't care, or doesn't know or care anything at all about printing. Nothing. All it does is it talks to the operating system. Hey, Mr. Operating System, I'd like to print something now. And the operating system says, sure, send it on, we'll do it. So this is the high-level concept of what layering is all about. Again, not rocket surgery. Okay. Individual layers basically can be swapped out. I can swap out a piece here. I can swap out a manager without too much trouble. A cool thing about when using this analogy, slightly different, talking about networking rather than printers. I could take, for example, the Ethernet chunk out and swap out a Wi-Fi chunk. I could swap a piece out, or maybe not swap them out, but switch from different types. So the layering allows for everything to continue to work even though the wire may have changed. That's the whole point here. Okay. A lot of people call this abstraction. Abstraction is one of those word that basically means don't bother me with the details, okay? Me, the user over here, trying to use my browser, me and the browser don't have to know anything at all about my printer. Likewise, using my browser through Windows, through my network card, if I was to switch from hardwired to wireless, my browser doesn't even care. It just says, okay, whatever, and it just continues to do its thing. Okay, so that's what that's all about. So here again is that abstraction. Here's an end user, and he's trying to use a browser. And here's the browser. And then somehow there's some software layering things that we're going to be talking a great deal about in this course. And there's a signal that gets sent over a wire. This guy doesn't know anything at all about how this works, which is perfectly okay. Now, you as a student might have to know, but the user of this technology doesn't have to know. That's abstraction. We don't have to know all of that stuff. Okay. They talk about the layering tasks. And basically, they talk about 5 tasks that typically the layering has to do. One is you have to be able to have user commands, some sort of a layer in there that says, fetch me this, or show me this picture, or listen to this music, something, right? And then they have to have some way of breaking it up into segments and reassembling it at the other end. That's another layer. And then some sort of way of identifying and locating and my destination. Something that says, well, the destination is real local here, or it's way far away, I need to do something different. Has to be some sort of error control that says, wait, I did not get packet number 408. Could you send me packet 408 again? Okay, something like that. And then last, the actual signaling. So that's the actual layers that we're going to be doing. They have some goofy little examples of how these 5 steps work. So specifying the user's needs. Okay, segmentation. So inside a packet, there's going to be some header information. It's going to be, what command am I after? Am I sending data? Am I Receiving data, what's the command? What's the sequence? Because remember, they're broken up into chunks and everyone has to be numbered. What's the address? Maybe like a checksum, some sort of a system that tells me if it's something broke, and then some sort of signaling. Here's what the actual honest-to-God packet looks like. And it's an envelope inside an envelope inside an envelope inside an envelope. It sounds a little crazy, but here's my application. It says get index.html, and that gets sent to the transport layer. Don't worry about what that is. We'll get to it. And this is sequence number 1839. And then it gets sent to the network. It says, here's the location. And then finally it gets onto the checksum for that packet, which is 43.95 in this particular case. So that's what that's all about. Okay. On page 23, they finally start talking about TCP/IP. A lot of people have heard the phrase TCP/IP, Transmission Control Protocol, and IP Protocol. And we're going to be spending an awful lot of time talking about that. Okay, so essentially, the layers for this TCP model have names. So layer 1 is the physical layer, and that's where the signaling, that's where the actual, the voltage varies on this frequency between plus 5 volts and minus 5 volts. That's the kind of signaling. Layer 2 is the data link layer. It has a name, and that's where the error control takes place. The network is about how do I get it from point A to point B. The transport is I need to break it up into chunks. I have to reassemble it at the other end. And then finally the application is whatever the heck the person's asking to do. Okay, so that's what TCP/IP. And you're going to need to know the names of these things. Yes, you are. So here's kind of another one. A same view, the physical layer, data link, the network, the transport, and the application. And here's some examples. So starting at the bottom. So the physical layers could be like a radio or a cell phone, or Manchester encoding is the type that's used on Ethernet cable. Sonnet is fiber optic cable. So basically this is the physical layer. This is how I impose a signal on the media. The data link could be things like Ethernet or Wi-Fi or asynchronous transfer mode. Network is probably always going to be IP. The transport of I'm not going to bother you with the alphabet soup because we got chapters that'll deal with that. And then the application layer is things like email and web and all the rest of those things. So that's how these things all fit in here. Okay. The next thing we're going to talk about is the OSI model, page 24. And this is the part where, you're going to have to know the OSI model. I'm sorry, this is one of those things you're just going to have to know. So, Open Systems Interconnect, OSI, proposed this model. And they call it a model on purpose. The model doesn't mean technology, okay? It doesn't mean you apply... a model is a logical view of network. It's not an implementation. You can't go and buy an OSI implementation. It doesn't exist. It's just a logical model. Okay. It was standardized by the ISO. And you go, wait a minute. OSI, ISO. Is that the same thing? No, they're not the same thing. Okay. And so it's just yet another layering scheme. Now, to help you remember there's these cool little mnemonics. And the one that I like, it says, please do not throw sausage pizza away. One more time. PDNTSPA. Please do not throw sausage pizza away. That's the way I was taught on how to remember the OSI model. Okay, we're at a good place to stop, and we'll pick this thing up in just a few.